is the last day we're moving out of my apartment. That's not. I just said today's the last day where I'm dealing with moving out of my old apartment. It's not the same thing as the last day where I'm moving into my new apartment. You know, there's just boxes everywhere.
So you already have the new apartment?
Yeah. It's on Marine Road, just like a block north of the 210.
Yeah.
It's like a 15-mile bike ride. What program do you use to make your slides?
TechMax.
TechMax.
Which I like. So the nice thing is that you can edit as you type. So then you can
Is it just for Apple products?
no, it's so you have accents. Yeah, lots of noise. So basically, it's a guy who rewrote LaTeX from scratch to make it interactive. It's not LaTeX, but the philosophy is quite similar. And everything is it's just basically it's LaTeX, except that you have access to all the boxes, and you can make consistent selections that will always span a given level. And actually, when you think about it, when you write LaTeX, most of the time you're spending, when you try to do copy paste, for instance, is identifying which levels of thing. So yeah, it's really nice. I started using it, and now I'm almost. It's also very nice for tables, because tables it may take alignment. Everything is missing. Just go on. But I'm using. It's my first time starting presentations. I use it most of the time for write-ups. And so it's called TechMax, but Max is not Mac. It's like Emacs. So it's more of a unique thing. And actually, the weakest thing in the software is the interface, which a different guy wrote. But the engine is incredible. And yeah, there are class files that are similar to those that you use for papers. So you can import your LaTeX file. I often do that for PRL, for instance, where you need to pick 4 pages. I import the LaTeX file. I just edit that, you see the TLS, and then I just export. Very quick. Okay, probably start in 2 minutes. And since you're you're not so many, so you should really feel free to interrupt and ask questions and things. You're probably from a little bit of diverse backgrounds. So, and there's not so much to cover today. Actually. So actually, I think I'm going to finish the lecture of last week to start with, which was about imperfection. So it's loosely connected to the main theme of today. So it's not strictly necessary, but it's nice. So remember last time we were with that equation for a strut on foundation, where lambda is the load parameter, which is the pre-stress here. And we were asking the question of what happens when you have an imperfection, and the idea of studying imperfection is that we are looking at a system that can bifurcate, so has zero stiffness, and there's a possible interaction between the imperfection and the particle. So we use a nonlinear equation that's a simple way of capturing a system that can buckle. And we use an imperfection in the boundary conditions that represents a strut that has a small kink here. So epsilon would be a slope here. And then we need an extra boundary condition, and we just use the natural one. So now we're considering a system that's we're assuming symmetry and considering half the domain. So the imperfection is now in the boundary condition. That's our epsilon. And we said that we could start to analyze that by linearizing, which makes sense because epsilon is small. And if you do that, you have an equation with constant coefficients, and you find exponentials and cosines and sines. So you have the solution in this form. And so you can write the dispersion equations, etc. And typically that's the type of solution that you get. So you have the initial imperfection here that damps out away from the origin. Now, what's interesting is if you go to values of the loading parameter where the system spontaneously buckles, so that's taking lambda close to 1. And then you can analyze this solution, and the important thing here is that the B parameter, which gives me the decay length of the solution, is going to 0. So B is the inverse of the length. Remember, I call eta was the expansion parameter in the Coulter expansion, and here we are with a symmetric bifurcation. So in that parabola for the perfect system, eta would be the arc length. So the increment of load, which I measure on the y-axis on the bifurcation diagram, is the square root of eta. So this eta here is just the square root of the increment. Okay, so B, you can analyze, there's an explicit solution, so this B goes to 0, like square root of 1 minus lambda. So square root of distance to threshold, which I call eta. And so you see that on numerical simulations, where for small lambda, you have a solution that damps out quickly, and for larger lambda, you have a blow up, so the amplitude of bifurcation goes to infinity, and also the damping is slower and slower. Okay, so that typical wavelength diverges. So it's typical of a singular perturbation phenomenon where there's an essential feature in the solution, so here length scale, that depends actively on the distance to threshold and so here is the solution that you get by this just simple linear analysis, that your actual mode is going to be a combination of the buckling mode, because the coefficient A goes to 1 when we are close to threshold. So here we recover the buckling mode, but then this buckling mode is modulated with a slow variable. So this x, because eta is also 0, x capital is called the slow variable, and that I call A. That would be the amplitude which you see. Okay? So it turns out that we've discovered this particular form of the solution in one example, but it's actually a very generic feature of systems that have an intrinsic length scale associated with buckling, that's the x here, and are much larger than this wavelength. So we call that extended systems. Extended system is systems whose length L is much larger than the natural wavelength. And whenever we find an extended systems, it will be, we'll see, I can give you a few examples that it's not sufficient to take the local buckling mode when you do post-bifurcation analysis. You must also remember that this buckling mode can be modulated by this slow variable. Okay, so now I switch to the nonlinear analysis of this imperfect strut. And I could continue this reasoning and do the Coiter analysis, and well, this would be along the same lines. But actually, I'm going to shift a little bit and actually use that idea of modulated solutions and port it to a slightly different context. So I'm now changing gear a little bit. And this idea is really at the core of localization. So here you start to see something that looks like what we've just plotted. At the bifurcation threshold, you have the regular, and again, that's experimental pictures of a thin film of polymer that's floating on water. So the water is really acting like a foundation. And you see that at the buckling threshold, you have a relatively uniform buckling amplitude. And then as you compress more and more, you see that it tends to localize. And that's really the type of phenomenon that we can capture by this amplitude equation. And I'll show you it's a simple generalization of the ideas we've just seen. So the idea here is that we seek the solution to our post-buckling problem in that special form, which is, again, specific to extended systems. In the extended system, we have the original variable x and the slow variable x capital. Okay? So x capital would be like that, where eta is our expansion parameter, you probably remember. And if you want, in non-extended system, we just have this. Okay? So now, and this term will be the one essentially we just found, right? So this would be locally the buckling mode that depends on x times an amplitude that depends on capital X. Okay, so that's the form we want to try in the Coiter expansion. So we generalize the Coiter expansion with that type of thing. And now you'll see that this guy, well, you have to think about it, how the expansion should be continued, but you can either do some test or some reasoning. But essentially, the expansion continues like that. So the only difference with respect to earlier is that we introduce an additional dependence on this variable x, which is ultimately related to the original. Okay, and again, that holds beyond the context of imperfections. I'm going to show you that even for a perfect system, it makes sense to use this kind of expansion, and you'll see the type of phenomena that are connected. So let's take this particular case of symmetric bifurcation for the strut, for instance. And the analysis we've just seen suggests that we should use this form of the slow variable, so that we have a scale which is inverse of our bifurcation parameter eta. And as soon as you start seeing this expansion, you see that we're really addressing singular perturbation, because if you take eta goes to 0 here, you would have this one would be 0, right? So it doesn't really, I mean, it doesn't really make sense. There's no, the passing to the limit is not a simple process. So the point again is that we have not considered that earlier, but that form is really what you want to consider in the Coiter expansion, and it really fits naturally in it. And also, it's incorrect, and I'll show you, it's actually incorrect in extended systems to ignore this term, which you would naturally do because it makes sense. So let me proceed and show you now. So, yeah, Sergio.
So the W1 you might find as an eigenvector, for example.
Right, so I'll come to that later. So it's a little bit abstract now. But essentially, W1 is going to be an amplitude depending on the slope variable times the local buckling node depending on this one. Pretty much like what we had.
The W2 also comes from analysis?
Yeah, by pushing the expansion to higher order. Yeah. And that's exactly the point. So yeah, I'm actually, so in the previous lectures, we were, solving this order by order, but we didn't have the X because the capital X, because we were not considering extended systems. So that's the Coiter method, which does the linear stability analysis here, and then has corrections here, and then you can also calculate the amplitude and stuff like that. So that's the Coiter method, but now it's extended in the presence of this slope variable. Okay, so let's take this system again. We are back to the perfect system, and I'll show you that this expansion is relevant here too. And we use so that's the equations of equilibrium. We have this expansion of the load, which we used as before, and now this new expansion of the solution. So what's new now is that the derivative of W with respect to X, which we did in this model, I wrote prime here, involves different terms. So I need to take the derivative with respect to lowercase x here, and this has two terms, right? That one term coming from here, which I denote as dW1 over d. No, sorry. Okay, I'm not expanding this. I'm just introducing notation for the moment. So I call dot the derivative with respect to the slope variable, and prime the partial derivative with respect to the fast prime. Right? And then when I need to calculate this one, it will have two terms, one coming from here and one coming from here. Okay. So and that's actually written here. Oh yeah, no, sorry. So this term here, when you take the space derivative, that's two contributions. But the point is that the one that depends on the slope variable gets multiplied by d uppercase x over d lowercase x, which is eta. So that puts me this second term one order further. So see, these are the two pieces coming from here, but they are shifted. One comes at the same order as before, and this one is shifted. Okay, so it's just algebra. And essentially, what we need to do is to insert these, these expressions of the W point in this expression and read order by order, as we did before. And the nice outcome and the nice result is that it's almost exactly like before, and there's only a very small change with respect to what we did before. So at linear order, you see that we don't change anything. And we find this linear operator times W1, which by construction is critical. So we still have that this W1 is the linear mode. But now this LC only involves derivative like prime, like this one with respect to x. So that's exactly like before, and there's no capital X problem. So the linear stability problem is like this. Next order, this is like before, only primes, and then we have these new terms. But what you can see here is that so this W1 will be essentially a cosine. So the prime will be essentially a sine, and that's going to be minus sine. So these two cancel out. You can check these. So this is actually 0, and nothing changes at this order. Well, actually, I'm solving this order by order. So the first equation is solved here, and this would be a1 of x times cosine. Okay, now let's look at what we have at the next order. we have this, which doesn't depend on dot derivatives, so on the derivative of the slope variable, and it's like before. So that's the piece you're used to up to here. We have this piece, which is like this one, evaluates to 0 if you do the math. And we have a new piece here. Okay? So now, we start by solving this as earlier, which gives us this form. It's exactly like before. Remember, in the linear bifurcation analysis, we had this A1, which was the amplitude of the node, which was undetermined at this order. But now it's just a function of x, of the slope variable. At the next order, we have to solve this, and I don't know if you remember, we did it already. We found that for this particularly simple system, everything cancels out at this order, and you can actually take W2 to be 0. So it's just simpler. Usually you have to determine W2, but it's now 0. So we know W2 it's 0, and actually we can find that lambda1 is 0. That's because it's a symmetric bifurcation. So that's exactly like before. And now you remember that we use the solvability condition for this equation by multiplying it by the cosine and taking the average to read off the value of lambda2. So we can do exactly like we did before. The only difference is that we have this extra term to account for. And this extra term has dot derivatives, so it means it has derivatives of the amplitude. So we do that, it's just averaging cosines and sines like we did before. And that's the equation we had before. We had these two pieces earlier. You recognize the bifurcation equation. The roots are A1 equals 0, that's the unbuckled solution, or A1 square equals something lambda2, that's the parabola. But now we have this extra term. Okay, so we would just arrive, and these are constant that you can easily evaluate. So that's the equation that you arrive with this new term. And you can do the trick that we did before. So that was obtained in the framework of an extension, but you can multiply by eta cubed to make it more readable. So eta squared times lambda2 is our increment of load. I call that delta lambda. And eta times A1 is the true amplitude. Right? So eta times A1, which is in this W1. So that's the true amplitude. So that's the bifurcation equation that we arrived to. We have the parabola like earlier, locally in some sense, but then we have this new term, which is associated with evolutions in the amplitude. Okay, so summary. We started with our now perfect nonlinear strut on the foundation, and we find that locally it's making oscillations, but now we have this amplitude and we have an equation for the amplitude. So we should be, just by solving this equation now, which only involves the long length scale, by solving this equation, we should be able to find the final solution of our problem. Okay, so I'm just repeating the fact that this derivation is essentially independent of whether we have an imperfection or not. And we are looking at it now in the case of a perfect system. Okay, so it's just a matter of solving this simple equation. And actually, I'm doing something now because it's more interesting. I'm changing the type of nonlinearity in the spring. So I'm going from a softening now to a stiffening nonlinearity. So if you look at what's happening, it changes the coefficient here. And we have a modified version of our amplitude equation. And this equation you recognize really looks like the equation of motion of a particle in a given potential. So that would be the acceleration term, and so that's connected to the potential. Right? So you can actually, that's called the dynamic analogy. So to solve this equation, we can use the analogy and then notice that we have a conserved mechanical energy that's made of kinetic energy and potential associated with this force. And so that's how the potential looks like. And now we are trying to find, if you replace space and time, we are essentially trying to find trajectories in this potential. So what are we looking at? we have to specify what would be the boundary conditions at infinity. So typically, if you think of the floating sheets problem, you will expect that the oscillations damp out at infinity, and that corresponds to motions where you start from this unstable equilibrium, you spend an infinite amount of time there, and then you're rolling back and forth into potential. I think that's what you get. It's called a soliton in some contexts. Okay, so you can solve this equation. You can do this by quadrature. I mean, it's just calculus. And you can have an explicit expression for that, for the A, which is this thing. So this thing is just the envelope that you see here, and it's the motion of the particle. And remember, that was the amplitude which we need to multiply by the cosine thing, which is the local, which is given by the regular mode. So at the end of the day, that's the solution of our buckling problem. That's the strut on the stiffening foundation. And so this is the solution. And again, you see that there's a length scale which is fixed and set by the linear buckling analysis. And there's another length scale here, which is the inverse of that guy. And the very important thing is that this depends on the buckling load. So if you go near the threshold, this could go to 0, and the length scale is infinite. So you have something which is uniform, and as you move away from the buckling threshold, that localizes because this increases. So the length scale associated with that is smaller and smaller. And on top of that, you have an extra dependence on the buckling load, which is the square root, and that's the classical amplitude which you expect for a symmetry bifurcation. Okay, so this solution does two important things. As you move away from the threshold, it increases in amplitude, but it also focuses more. And that's exactly what you see for the sheets here. Decreasing amplitude, and it localizes more. So all that comes from a straightforward, or natural, I would say, natural extension of the Coiter analysis. So then these people had a science paper showing, based on numerical simulations, that you can correct. Well, they were essentially characterizing the displacement force for this system, and they get this parabola, and the parabola is just actually a direct consequence of this equation. So it's fully in line with what other people have done in, well, not in this fluid context, but in what's called localized. And when you know these solutions, and when you know that localization is possible, there are many other systems that actually localize. So this example is numerical simulations we've done on an elastic knot, sorry, on a knot that slides on an elastic rod, and then we were applying twist, and we were observing that at some point, if you apply some twist, it stops to rotate by a large amount. And actually, this can be understood as a very similar system as what we had before. So the only thing that the knot is doing is introducing an imperfection, because when you want to enter the knot, you need a small angle to get into the loop and connect with the rest. So the knot is really acting like, you can erase the knot and replace it with a small kink here. And you can calculate the kink angle by looking in details at what happened here, but that's mostly irrelevant. And so now we have a twisted rod that has a small kink. And it's exactly like the strut on the foundation that had a small kink. Remember, when it's close to bifurcation, it becomes highly susceptible. There is the same. We have a torsional instability. It's possible to do helical buckling with a rod. And so when we are close to the helical buckling, this small imperfection triggers some large type of deformation. So it looks like a complicated thing, but it's actually very similar to the strut on the foundation.
What determines the size of the knot?
Well, it's actually how much you're pulling. If you don't have friction, there would be how much pulling force you can. There's a simple energetic argument that where you balance the bending energy which is in there with the pulling force, and you get the radius as a function of the pulling force. Yeah. Okay. So conclusion for localization, and the next lecture will actually build on top of that, is that the amplitude equation, we've seen many variants of this amplitude equation. So the simplest form would be just these two terms for how the amplitude depends on the incremental load with respect to the threshold. Then we had an extra term that accounts for imperfections, if you remember. And we have yet another term which accounts for modulation and localization in extended systems. But that's all derived in a consistent setting by doing this systematic Fourier expansion. And then associated with that, there's a biaxial structure, so you define an energy and essentially solve a much simpler problem than the original one. And yeah, then essentially what we've done are particular cases of this equation. When you kill all the terms and retain this one, you find that it has a solution only when delta and equals 0. That's essentially the linear bifurcation analysis, where I only retain linear terms. You can do the response to a harmonic imperfection, or you retain all these three terms. That's what we did in the second part of the lecture, and then the imperfections. Okay. Okay, so now on to lecture 5, and it's good because we've almost kept at the pace. So we're back on track for the next lecture. Okay, so I wanted to talk about material instabilities, and I give you here several examples of systems that tend to produce localization, meaning that they feature solutions that are uniform and different in different regions of space with some interfaces or boundaries connecting to it. So one example is the liquid vapor interface, where we have a low density and a high density regions, and on average you can expect some is dependent on the particle density. You can find shear bands in composites. Plastic necking, which is a little bit of an extreme example of that, because as you start to go through localization and as you start to produce interfaces, you actually go to breakage. There's this nice example of, it's an old paper by Baron-Blatt, where they're just pulling on the rod made of polymer thing, and it's actually similar to a phase transforming material, and you're going to have two phases which are well defined. But we all know of these party balloons, where, well, depending on the constitutive load of the balloons, typically what you get is two phases for some range of pressures, two phases, one that has a large radius, one that has a small radius, and this connecting region, and tape springs, which Sergio and other people have studied, where you have regions of high curvature and regions of low curvature that coexist. So all that comes from the same framework, basically, if you think mathematically. So the crucial ingredient is some energy that depends on the local variable lambda and is non-convex. That has two wells. So typically that would represent the liquid and the gas phase, if you're thinking of the Van der Waals model. So there's an extra load parameter that would be the pressure for the phase transformation that's conjugate to this variable lambda. So well, I'm not sure if I should speak of the liquid gas model or bar. I probably switch to a bar, which I'm more familiar with. So for a bar, lambda would be the local stretch, and F would be the external force, right? So F times the integral of lambda would be the potential energy associated with the force. So these are the two main ingredients, and because this one is non-convex, has two wells, you find that we see that you cannot describe interfaces and phase boundaries with this model, and so you need to add some kind of effect that takes into account gradients of lambda, and the generic way that you can do that is by adding this energy penalization associated with gradients of lambda. So when you do that, this epsilon can be interpreted as the square of a microscopic length. often people just introduce this heuristically. I'll show you in the next slide how it's actually possible to deduce this kind of model by using expansions. And essentially that applies to all the systems here. And just, we need to be a little bit more general, so we need to assume that this epsilon here is actually a function of lambda. So it's a minor thing, it doesn't change much, but it's relevant to many situations. So first question is, how can we get this type of model? And that's a paper with almost submitted with my student Pierre Lestringal. So the idea here was to start from a model for axisymmetric membranes. So that would be the balloon, right? And people have done that. People have used this model for axisymmetric membranes and simulated propagating bulges. But the question I'm asking here is, can we establish a connection between this model and the one from the previous slide here? Because that one has been extensively studied and is well known to lead to this kind of localization phenomena. So it would be nice to not redo the analysis from scratch with a different model each time and just show that this model connects with the other one. So this can be done. Well, let me first give you a few details on how this is formulated. So the main unknown, so that's the reference configuration, that would be the deformed configuration. I take a point capital Z in reference configuration into a new configuration, which would be lowercase z as a function of uppercase z. So that's my transformation. And I also have a change of radius, which I quantified by mu. And mu is the hoop stress, right? So that's the ratio of the deformed to the undeformed radius. So my two main unknowns would be lowercase z and mu as a function of capital Z. Now the first thing I do is that I introduce some kind of stretch, lambda, which is this derivative. So that tells me if I project everything on the axis, what would be the stretch here. But that's not the true stretch, because the true stretch has to be measured along this direction. So that's kind of an effective stretch, right? And I have two strain variables now. Now the membrane model is formulated by first looking at the strain measures for the membrane. So one strain measure is, well, actually the indices are reversed. I see that now, so how should I? So in the hook direction, in the orthoradial direction, the strain measure is just given by this mu. And in the axial direction, I need to measure the stretch, and essentially I have to write Pythagorean theorem. And I have a small thing. I expand this extension as something horizontal plus something vertical. So essentially, the horizontal part is this lambda, and the vertical one is mu prime. Okay, so that would be my definition of strain. In terms of strain, I can write the elastic energy of the membrane. That would be a finite elasticity model for the membrane. Then I add pressure times the volume. Right. Volume is lambda d capital Z, that's the length of a small element. And mu square is the change of area, so that's the volume. And that would be the pulling force. Well, actually, in that setting, there are also pulling, and there are experiments like that that actually pull on the balloon that provides an additional control parameter. Okay, so that's the classical membrane model. Now, the trick is to focus on slowly varying solutions, so that's debatable approximation, but mathematically provides a way to solve that by expansion. So I'm saying debatable because when you have a real phase boundary here, nothing tells you that this mu prime is going to be small, but at least you can try and see what you get. So at some sense, at the end, we need to verify that the solutions based on these assumptions are consistent with what we see in the experiments or simulate based on full model. Okay, so if you insert that into here and expand, you have one part that only depends on this thing. So that's considered as a dominant term. You put in here, and all this then becomes a function of lambda. Okay, and that typically that's exactly what you do when you analyze homogeneous solutions. uniform solutions, which is what people usually do at an introductory level for the balloon. And this is this G naught, so it's a potential. But then you can also take this as a correction and expand this guy around this with this as a perturbation, and that's what you get. Okay, you need the gradient of the strain energy with respect to the strain, so that's called the pure Kirchhoff stress, times this correction, which is essentially mu prime square. Okay, so now we have a nice model, but you can see that. So this one is essentially mu prime squared. There's no derivative with respect to lambda, so you would actually, it would be nice to get rid of lambda, so you can relax, do an optimization with respect to lambda. And what you find here is that to first order, you want to cancel the gradient of this, and then you have corrections that come from that. But essentially, lambda must be found by the condition that this is the gradient of this guy with respect to lambda is 0. And that's again exactly what you do when you analyze homogeneous solutions. So you can estimate this lambda as being the one predicted by the analysis of homogeneous solution. And then you can just insert this expansion into this one, check the orders, etc., etc. And so with lambda given by this formula, this is now a potential that only depends on mu.
Don't you have multiple solutions?
Sorry. Well, no, I'm still keeping the dependence on mu, so I haven't optimized with respect to mu. It's only when you optimize with respect to mu that you find the true Waals. So actually, this G naught, skipping ahead, this G naught of mu is really like the this W of lambda. Sorry that the variable names have been switched. Lambda has become mu now. Okay, so if you do that, you end up with this potential, which you can predict by, which basically everyone knows by the analysis of homogeneous solutions. But now the more interesting part is that you have an explicit form of this thing. So this is the pure Kirchhoff stress in the homogeneous solution, which is not so difficult to estimate, and it gets multiplied by mu prime squared. So you have an explicit expression of what your regularizing term here is. If you switch again, u and lambda. So that's one example where you start from a specific system, and by doing some kind of expansion, you can actually prove that. And actually, we were the first one to be surprised by this. If you use this model, which is based on this approximation, and use it to simulate well-formed bulges and relatively sharp interfaces, it just works remarkably well. It's very difficult to see the difference between the solutions from the original model and this one. So this approximation, I don't know exactly why, but it works really incredibly well. Okay, so now let's go back to this model, which I now view as generic for all these phenomena, and try to solve it and see what would be its solutions in various ways. So the first thing we can do, and okay, so probably some of you are, or maybe most of you are familiar with that, not sure. So I'll assume not, but so who has seen that before? 3 non-shy people, 4 non-shy people. Okay, so let me go quickly through that. So I'm just focusing on a specific type of solutions, and I'm looking at homogeneous solutions. When lambda is not a function of x, I got the lambda h like homogeneous. Then the energy boils down to that. The gradient term is not playing any role. And I want to optimize this with respect to lambda. I want to find the optimum of the energy. So taking the derivative with respect to lambda gives me that f is equal to the derivative of this guy, which I call m naught. Okay, again, this potential is given. So you can plot the derivative, and typically it's like that when you start from that. And so all these curves correspond to homogeneous solutions. Now you can ask whether they will be stable, and well, stable just has to do. You just need to ask whether, at least if you want, for stability, we start by looking at homogeneous perturbations. So the question is whether this is a minimum or not. It's relatively simple to do, and it actually can be discussed graphically. I forgot to mention that this has a simple interpretation. So n naught being the derivative of the strain energy of my car, that would be the internal force given by the constant flow. Right, which if I specify a material model W naught, I get this as the internal force, and then the internal force has to be balanced with the force on the plane. Okay, so that's an equilibrium of the bond. Now I can look at what the total energy looks like for different values of F. So now I'm changing F, which is the imposed force, and I'm picking the corresponding lambda that's sitting on the curve, and then I'm plotting this curve here, which is the total potential. So if you think about it, you go from a situation for low lambda, where you look pretty much like that, where you have a minimum, and that's a second equilibrium which is just appearing because I'm reaching this point here. So this one is a minimum, and it's represented here in green. And I have another equilibrium which is appearing. For intermediate values here, I have one minimum, one unstable maximum, and one local minimum. So green here would be absolute minimum. Purple would be local minimum, but not the absolute one. Red, which are the central solutions, would be unstable minimum, etc. Okay, so bottom line is that what you expect to see in real experiments are these parts, which are definitely the absolute minimums, these ones, which are metastable, and not this one. Okay, now the next step, once we've done homogeneous solutions, is to remember that we are looking at systems that typically have different phases. So typical solution that we expect for lambda would be like that. And the first thing is that we are forgetting about the interface, and we look for solutions that this way. So we ignore the gradient term. It's called the non-regularized model, and then the energy just looks like that, right? So theta would be the fraction of what is in the phase A. So then 1 minus theta is in the other phase, and then that's what my energy looks like here. If I ignore this term for the moment, I will restore it later, and integrate that with the fractions theta and 1 minus theta. So this is this, and so now I have a new energy which I can try to optimize with respect to the fractions and the two lambda A and lambda. So just by requiring that this is stationary with respect to lambda A or lambda B, I find the same conditions as before, so that the local internal forces in every phase has to be equilibrated with the external force F. I'm calling Fm the solution of all these systems. So that's the condition with respect to the lambda i's. I should also find some kind of chemical potential where I'm requesting that the energy is stationary when I change B into A or vice versa. So that's the optimization of theta, and the condition I get is this one. So I find that this new potential here in phase A has to match the potential in phase B, which is an extra condition. So now I'm looking for solutions lambda A, lambda B of these three equations. So the lambda A, lambda B, and theta of these three equations. And it can actually be done graphically, and it's quite nice. It's known as the Maxwell construction. So we'll assume that lambda A is smaller than lambda B. And I didn't. So we want lambda A and lambda B to match the same force F by this equation. And I didn't try to use lambda here because we know it's a phase which is unstable. So that would be that would be sitting on the maximum of energy, and you can easily show that it makes everything unstable. So I'm purposely picking lambda A and lambda B on these two branches. So now we have to deal with this, And this has actually a simple interpretation. By just rewriting that, you can show that just by rewriting the terms, this has to be equal to f times this. But it's also easy to show. If you remember that, oh, there's a knot missing here. If you remember that W naught is actually the integral of n naught, you can write this difference as the integral. And then if you equate this and this, you find that f has to be the average of n between lambda A and lambda B. So graphically, what that means is that this has to be the average of that function. Okay? And this also means that the area here and here have to be the same. So bottom line is that there's only one way that you can make mixtures an equilibrium. It's only possible at the specific value of the force where that divides these two parts in equal areas, and then there's a single A and B phases, right? So in general, when you start with these models, unless you have multiple up and downs, but for just a single one, there's only one possible way to have phases. Okay, and so when you look at this W minus lambda F, which is exactly that, then that's the case where you have a two-well potential with the two wells exactly aligned. That would be an interpretation of this form. Okay, that actually, I'm going to skip this. That actually belongs to the previous slides. That's a mistake. Okay, so now we have characterized mixtures. We have one special value of the force called the Maxwell force, and that's basically all we can say in this non-regularized model where we have to take epsilon to be 0. We are ignoring interfaces. One drawback of this model is that it completely ignores interfaces, and actually the only thing we can characterize is the concentration of A and B. There's no way we can tell where A and B are in space. And actually, since there's no penalization associated with phase boundaries, this model could predict that you have infinitely fine mixture of A and B, which is not typically what we see. So in other words, a notion that's missing here is the notion of surface tension, and for that we need to restore the epsilon. Okay, so let's go back to the regularized model and see now what would be its typical features and what we can learn by restoring this term, building up on what we know from the approximate analysis of the previous slides. So you can do the calculus of variations, the virtual work, and derive equilibrium equations for this system. It's just well, there's an extra complication which is often not accounted for that because of this dependence on lambda. You have extra terms here, but you can do the math, and typically that would be the local equation of equilibrium that needs to be solved for that. You can expand the derivative and write this form. So this form is like before, when we ignore epsilon. So that would be the local equilibrium in the homogeneous space. And then we have the gradient effect here, which adds two terms. So it makes my equation of equilibrium, it's no longer an algebraic equation, it's now a differential equation of order 2, and I need to solve with two boundary equations. But I know everything, so you can do numerical simulations of this equation. And typically, that's the type of solutions that you get. So let me explain. So typically, a solution of this equation would actually look like what you expect. It connects two phases, lambda A and lambda B, which are consistent with the ones we predicted previously and showed that. And then by solving this differential equation, you can resolve the interfaces typically. And this is typically the bifurcation diagram that you would get for such solutions. So here I'm plotting the average value of lambda. And that would be the force. Okay, so I'll come back to this. I just want to show you this for the moment, and we'll see how this is connected. Okay, so just a small trick that's useful for later. you can actually notice that this equation has a first integral. So you can easily check that the derivative of this thing gives you that back. And you can, well, it's not so much of a good news actually, because practically that's, it's even hopeless to use this to construct the phase diagram. Because, so typically when you have the first integral, you would separate lambda on one side and f on the other, and well, the d lambda on one side and the dx on the other side, and do quadratures. But it doesn't work at all with this problem. So actually, we spare that, we'll use it at some point, but that it's actually a bad idea to try to use this to build that. Plain numerical simulations that start from that are actually much easier. The reason is that the integrals you end up calculating for this problem are close to a singular point, and it's just terrible numeric. So sometimes things that look nice and simple turn out to be not so nice for numeric. Okay, and then typically what we expect is that we have internal layers, so where things change relatively rapidly, where this term plays a role, and away from that, not really. Okay, so let me now try to focus on something specific with this, with always the same model. I want to describe what's happening now in an infinite medium, because it's simpler, and try to describe it. So specifically, I'm looking for solutions that would tend to two different concentrations on the two sides of the domain, and see what I can learn from them. Okay, so remember, we have this invariant, so that we call C its constant value. I can rewrite, sorry, and I'm going to find the value of C by using the boundary condition. So what I'm expecting here is that at the boundaries, this term is 0, because we are connecting with the constant solution. So I can calculate C as these terms with lambda replaced by lambda A or lambda B should be the same. Okay, and if you have that, you know that actually this equality is the one we've seen before when we were ignoring interfaces. The equality of these two things means that we have to be at the Maxwell load. So that's there's this connection between this microscopic description of the interface and the macroscopic one. To be consistent, the microscopic model can only connect with the solution of Maxwell. Go back. Why did this invariant come from? Integrate twice. So I have a second order ODE, which can be integrated out with this invariant. Actually comes from the variation structure. It's like the, I think it's like the Lagrangian and the total energy. Right?
Also, this is the compound.
Sorry?
Oh, sorry, I was thinking of the compound.
Okay.
This is the compound second order, right?
Right. Yeah, not forced. Okay, so we recovered this equation which we know from before, and then if you know C, you can extract lambda prime, and you can do this method of quadrature. So essentially, you have minus epsilon plus something that depends on lambda equals 0. So you can separate this out as d lambda over something that depends on lambda equals something that depends on dx, and if you do the math, that's what you get. It's fine. So that's the quadrature method. You just have to integrate this So it's just an integral to calculate, and then you have the solution. So that I'm skipping. But essentially, you can check that everything works fine, and you end up with this type of solution. I'm skipping the details. You can check also how that connects, and you can show that it's exponentially damped here, so it's a very quick damping. And now we can return to our original question and look at, well, the question of can we predict a surface tension or something associated with that. So now let's look at the energy of our solution. It turns out that you can rewrite it nicely using what we've seen before. So you can substitute this term with the C, for instance, and rearrange things, and you can split the energy in two parts. So this C here is just the energy of phases. So that's what we would guess from the macroscopic model. And the interesting part is that we have a new contribution which is fixed. I mean, that's just a number, right? I mean, that in principle gives you the solution lambda of x. So you know lambda prime. You need to calculate that from the model. And that's a fixed energy, right? So that's the fixed energy which is hidden or which is associated with the interface. So if you step back and look at this from a microscopic view, we've just been able to introduce some kind of surface tension in the energy, which is associated with this gradient effect. It scales like epsilon. Okay, now we are in a 1D situation where the interface energy is just a constant. In 2D, you would have some constant multiplied by the area, which is more. Sorry, in 3D, that would be the constant multiplied by the area, which is the more familiar situation. So it's just a little bit special because we're working in 1D. Okay. So we have surface tension in this model. Now we can try to do stability and bifurcation analysis. And actually, I realized only very lately that all the tools that we've seen before with Goiter and things applies naturally to that and gives you a complete picture of this system, which is quite nice. So let's take an infinite medium. Let me get back to the homogeneous phase. And let me ask whether I can do bifurcation. I don't have stability in mind because I can't really do stability, but at least we can see if we can bifurcate from that. So do we have neighboring solutions? And usually stability comes on top of that really easy. So we start from the energy. We do the first variation, which is another way of writing the equations of equilibrium we've had before. We look at the base solution, which is now the constant, and we linearize the equilibrium as we did before. So now we have two linear increments, virtual change, real change, which I call lambda one, and that's the equation we need to solve once we put them in strong form. So these are constants, they don't depend on x. And you recognize a second order equation with constant coefficients. So if you integrate by parts, you have minus epsilon h lambda 1 second was the homogeneous solution, another coefficient times lambda 1 0. So you know that you have sine and cosine solution. You know that the first solution that becomes unstable is the one with the longest wavelength, and here we're in an infinite medium. So actually the wavelength is going to be infinite, and the first bifurcation mode is just going to be lambda 1 so that's q equals 0. Wavelength equals 0. Okay, so it's a solution of this equation. And you find that this is possible whenever this goes to 0. So let's see where this happens. Well, this happens actually, so remember the derivative of W is called N0. So the second derivative is going to cancel whenever N0 is a maximum or a minimum. So it means that on this curve here, where we have the catalog of homogeneous solutions that can exist under different forces, we expect the bifurcation to take place here and here in the infinite system. Okay? So you've seen the tools of nonlinear expansions, and we can now ask, well, actually, and something we should say is that it's not very, the buckling mode is not very informative, right? It's a constant thing. And actually we'll see that because we have localization and modulation, the actual mode shape is completely different of that. So that's not very informative. Okay, so we have a bifurcation point. We can use the corridor expansion and do the nonlinear analysis. We have to remember that we are in an extended medium. It's long, we are in an infinite situation here, so we could introduce a slow variable, do everything, and the calculation, and we have the rest. But actually, in the simple setting, there's a much more elegant and simple method that we can use. And so this is how it reads. So take this, which is the energy of our system, and now we are trying to work and guess a branch from this point. So that would be F, that would be lambda. I use stars for the points where the bifurcation is taking place. So now I'm trying to build a branch here by hand. I don't want to use the corridor method. So I'm just trying to expand lambda and F close to the point where the bifurcation takes place, and so these L and F would be small things. So I just insert here, and that's what I get. So lambda is a constant plus L, so this gives me L times squared. And now I expand this. So I get all the star quantities when I'm exactly sitting at the point. So that's W star minus F star, lambda star. Now that's a constant. The energy I can get rid of. What do I get next? I get things which come from the expansion of lambda here. So I get the Taylor expansion of W dot. So I have the derivative of W, which is n naught, times the increment of lambda, which is L. That would be the first term in the Taylor expansion. The second term would be the second derivative times L squared, and the third term. But that, remember, is 0. We've seen that this was 0 at the bifurcation point. So that's actually 0. Next, we have things that come from the expansion of this term. We have F star times the increment of lambda. And we have lambda star times the increment of F. And then we have the other term, which is the product of the increments. Expand out to the product. Okay? So that's nice because almost everything cancels out. This is 0. Well, that's a constant, so we don't need to keep it. That's the condition of equilibrium, which we've used many times at the bifurcation point. That's the condition which we got from the linear stability analysis, which is required if we want to start to, to find a branch that comes out from this point, so that's also 0. And that's a function of the load, but not of the solution L, so you can also treat it as a constant. So we are left with this nice little equation. Okay, so remember, we are trying to build nonlinear solution. We are expanding nonlinearly. I didn't prove that I can discard the other terms, but I'm just going to. And now we want to find the solutions that make this energy stationary, and that's probably going to be a good approximations of whatever is happening here along this branch when things depart from being homogeneous. Okay, so it's nice because you have 3 terms, and you can do a scaling analysis. You have one term which has the gradients of L. You have one term which is a nonlinear term in L. And you have another term that depends on the load. So you can try to balance everything so, and see what scales come out. So so L would be, now means the scale of L, and delta would be the scale of X. Okay, so that would be typically my interface. So what do I get from that? This term is roughly, well, let me drop the 2 factor here. This is the estimate for this term, that's the estimate for this term, and that's the estimate for this term. I've chosen to put the 2 factor here because I wanted specific coefficients for my dimensionless formula, but you can forget about it. Okay, now let's see. By balancing these 2, you get the scale for L. Interesting is that the scale for L depends on F, which which is the distance to the threshold. So I'm starting to get the amplitude of my correction, my perturbation as a function of the distance to the threshold. Recognize this? This is the buckling amplitude, it's distance to the threshold. We seem to be dealing with the symmetry bifurcation. Okay? But more than that, I have this term which you might have recognized as our amplitude equation from the end of the last lecture. That's a modulation term, which we derived directly. That gives me a scale delta, which goes like that. And that's very interesting way. So we have a scale that depends like the power -1/4 of the distance to threshold. So that's something that massively localizes. This one is infinite, this scale is infinite at threshold. But if you're just 1,000th, if you increase the force or decrease the force by 1,000th, this is going to be 0.1. Right? So that's something that varies so fast with the distance to threshold that that points to a specific phenomenon of localization that's really strong. Okay, so this is just the scaling. So I have a scale for L and I have a scale for X. And that suggests, as usual, rescaling. I'm trying to look at, to search my perturbation as the scale I've just introduced times, sorry, the scale I've just introduced, which I can write like that. That would be by X. This one would be divided by the scale. So the usual business with scale. And the benefit when you rescale is that you get rid of all the coefficients. You have a simple equation.
So all these phenomena of localization boil down more or less to boundary layers at the end?
In some sense, yeah, it's related to boundary layers. Yeah.
In the same way you could define that inside a region you're going to have a certain dominant balance. And out of that you can get rid of other terms.
Right. Yeah, exactly. That's a refined. Well, I mean, but the trick here is that so it looks like a boundary layer equation, and there's definitely a boundary layer or something happening here localized. The trick here, which is not usually the case, is that we have some extra dependence on the distance to threshold. So things move and change in nature when you move away from threshold, and that's what's specific. But I mean, yeah, many of the ideas are connected. So we have this rescaled equation, and then it's always the same business. There's a dynamic analogy. It looks like the motion of a particle in the potential. The potential now is different. And actually, you can plot the potential. This is this. I don't know why my axis has been selected. It should be vertical. The potential is cubic now, and we are looking for motions in this potential that essentially do not blow up. So there are three possibilities. One is sitting on the unstable thing here. One is sitting on the stable equilibrium here. And then that's, it's of motions, right? It's equilibrium position. So that corresponds to L not depending on X. So that corresponds to homogeneous solutions. Well, remember we are at the top of this curve here. So we found that by decreasing F, we recover the two constant solutions here. So this would be my two equilibrium. Then there's another solution which is more interesting, which means starting out from here with a zero velocity, falling in the well and coming back with an infinite time. And guys, that gives me a localized solution like that. Okay. Remember that's in scaled variables. So we have actually stretched both amplitude and X variable. So if you look at the true, I mean, in real variable, what this means, so this bump, this soliton has a height that's given by the square root from distance to threshold and localizes as you move away from threshold with that typical -1/4 power. So that's something that localizes very quickly. Okay, we start out. So the init, if you want very close to bifurcation threshold, you have something like that, and as soon as you move, you have something like that. As soon as you decrease the load, we have this. So the last thing we need here is to see how this can be represented in a phase diagram. So we want to include these solutions in the phase diagram, and so we are in an infinite system, so let's use now the average of lambda on the y-axis, on the x-axis, so we can superimpose with the homogeneous solutions, and f on the vertical axis. So the question is, we have this solution that's localized, what would be the average value of lambda? Actually, we are in an infinite medium, so everything is dominated by what happens here. You don't see this thing in the diagram, and the branch that corresponds to that, I mean, in this particular set of variables, is just superimposed this branch. Okay, so in this, with this choice of variable, we don't see the interesting thing, which is the localized solution. Okay, so here is the picture we arrived to. We have this set of homogeneous solutions. We know that this part is unstable, and exactly at the point where it becomes unstable, there's a bifurcation point. And a new branch here, which you can't resolve in that set of variables, but it's nevertheless a new branch. You start here with the solution A, which is this one. It's a weakly localized thing. And very quickly, as you move here, it gets localized, and that would be the B. So it gets more localized, it grows in amplitude. And at some point, if you continue, you will eventually get to the Maxwell amplitude. And you know that at the Maxwell amplitude, we have solutions for interfaces, right, that look like that. So what happens is that this solution B, when you get to the Maxwell amplitude, becomes propagative. So it splits, and then it gets two paths that propagate. And as you move here, what's happening is that you have these two fronts that move away from each other. So you increase the concentration of B with respect to A, and the average value of lambda departs from A and goes to that of B at this constant. Okay, so you have localization first and then propagation. Does that make sense? Okay, so localization is really sits at a given place, and propagation means that you have a significant fraction of B now in your set. And then the same thing happens on the other side. Okay, you can visualize these things differently in this space, so that would be lambda and lambda prime, two stable points with the A and B, and as you increase the load, you do the circles, and that's a different representation. Okay, so now the question, we've studied the infinite length scale case in detail. What happens now when I have a system that's finite? And so you need to specify boundary conditions. And let me take, so easiest is to take the natural boundary condition that you get from the variational formula. So you typically assume that lambda prime is 0 on both ends. I'll come to that later. So just to give you an outline of what's coming next. So here is here is what the phase diagram looks like. That would be these green curves. And so this is typically what happens to the curve when the length goes to infinity. That's from it's infinity. So you get something like that for finite length, and that connects nicely with the infinite length case because everything gets squeezed in these corners. Okay, so that's the typical shapes that you and typically well, actually what matters is the slenderness parameter, which is the ratio of the actual length to this microscopic length. And that's really the parameter that matters. So when L goes to infinity or epsilon goes to 0, you go from solutions that are strongly penalized by the gradients that are not so steep to these sharp interfaces. That's your control parameter. And also in the system, there are different modes. So remember, we were starting with this mode here. If you do the linear stability analysis, you have actually several bifurcation points. The thing is that they're all collapsed in a single point in the infinitely long case, so that's a little bit splitting. But in the finite case, you have a series of bifurcation that corresponds to different modes. So I mostly focus on the first branch, and the other ones can be dealt with similarly. So let's see what happens now, and if we learn anything else by redoing the linear stability analysis and the business we've set up before, now in this finite length case and see what we've done. So you can do the linearized equilibrium, and you end up with the same equation that we had before. We put it somewhere. This one. Same equation that we had before for the linear stability analysis, but now with boundary conditions. So I use specific boundary conditions, and you have modes in cosine thing. So you can plug in this linear mode, you get the dispersion relation that looks like that. Okay, so this is the coefficient which I have an equation here. This is the other coefficient I have in the equation, and that's q squared. That's the classical bifurcation equation. Okay, so you can restore. Actually, remember that for in the infinite case, this was 0. Okay. And so you can guess that for a long bar, this is going to be small, meaning that this will have to sit close to the previous bifurcation point. So you can assume that you can actually expand this near this point here, which I call considers points. And so this, because it cancels here, you can approximate as the third derivative times the increment of load here. And this delta lambda now is how much extra load I can apply before the finite length system bifurcates with respect to the case of an infinite system. Okay, so this equation connects the delay in bifurcation caused by the finite length and the length of the bond. You see that the delay goes to 0. Okay. So a typical effect associated with finite length is that you move the bifurcation point a little bit away into the zone that used to be unstable. So you restabilize a little bit of this region here. The region it is restabilized is that now it's finite length and there's an energetic cost associated with gradients. So the modes that you had from the previous analysis in infinite length is no longer relevant. Okay, but other than that, we have this point here, and we have the, let's say, the first mode here by taking I equals 1. You can do the analysis, which is now nonlinear. I'm going to skip over the details. Now it's a finite length system. We have a bifurcation mode, which is whose wavelength is the length of the system. It's not an extended system. We can only express one single wavelength. There's no point trying to introduce localization and modulating amplitude. It's a regular Coiter analysis. So you can do the regular Coiter analysis. You can work on the details, and you find the initial slopes here. Okay. So it's a little bit surprising because it's a finite bifurcation, but you find it's a symmetric bifurcation, and you find finite slopes, but that's just because we are using a specific set of parameters. I'm going to forget about that. And it's the usual boring things. We've seen it so many times. With all that, you can calculate the amplitude of buckling as a function of distance to threshold, and you end up with a formula. Okay. Okay, so and there's no localization here. Okay, so you can find the start of this branch, and that's what you get. So it's not very interesting. But now, if you recall what we've done before, so we have two cases, right? So and they don't exactly agree. We have the infinite case where we have a localizing solution that has a typical scale delta, remember, which varies tremendously close to thresholds. That delta starts out infinite and then focuses very quickly. That's what we predicted based on the infinite case. For the finite case, we have a boring cosine mode, no localization. So the question is, how are the two consistent? We've lost localization here, and we can't account for a finite system here. Well, the answer is, of course, if we want to reconcile the two, we need to compare the true length of the system and the localization length predicted by the infinite analysis, right? So we can analyze this ratio, L over delta. Delta, remember, is like distance to threshold to the power 1/4, and then there are different situations. If L is much larger than delta, then effectively our medium is infinite. That's the drawing I have here. And it's so much larger than delta, then the actual boundary conditions I'm applying don't matter. If L is much less than delta, then this approach is probably fine. And now you can see that there's some intermediate regime which I don't think is known. I should check, but I don't think it's been studied, where both matters, right? And you can do some kind of improved theory where essentially you can redo the previous analysis, remember, of the dynamic energy, but now in a system with a finite length, so in rescale variables, the new x bar should not be larger than this number. So you can modify the solution that we get from the infinite case to take this parameter into account. And if you do that, I've not done it, you get a new solution that depends as earlier on the scaled slow variable, but now has an extra dependence on this extra parameter. And that will connect nicely to the two cases we had before. So it's another example, pretty much like in the boundary layer, right? That's like outer solutions, and we're trying to find an improved model that can handle both situations. If you do that, that can be solved. It's just a simple thing. It's a little bit painful to take into account the boundary conditions, but an explicit form of this can be found. And then you can reconcile everything. So if you have this, you'll find that you start with a cosine mode predicted by the finite length thing, but very quickly, because that happens very fast when you increase the load, this cosine mode will eventually focus and overlaps, right? So both theories were true, and actually, the cosine mode is even, I guess, a little bit misleading because its domain of validity is so limited here because of this power that it gives you only it's asymptotically correct, but it's an incredibly narrow range of validity. And something improved like that is actually much more relevant. Okay. So I think we've covered this diagram at length. What I like is that, well, first, it's completely general. It applies to many situations. But it's also a very nice playground for using these bifurcation methods, localization. And in particular, it's, if you think in terms of classical bifurcation and you see cosine mode, it's hard to connect how that can, I mean, it's hard to realize how that can connect to localized solutions. For that, the multiple scale expansions and these things are connected. So really the specific feature of this system is that it starts out here as a cosine mode and very quickly gives rise to interface as you move a little bit around this bifurcated branch. So at the end of the day, the picture we come up with is homogeneous solution that are stable here and here, a little bit past the maximum due to a finite length defect, an unstable region in the middle, and that bifurcated branch here that has localizing and then propagating solutions. If you look at stability, it's exactly what you expect. So the stability changes at 4 points, and typically what you get when you increase, so let's say you control the total length, you control the average stretch, you would go on this branch, skip on this branch, do some propagation, and then connect back. Or if you do the force-controlled experiments, so you're putting a constant force, you would go on this branch up here, so you don't see localized solution, you skip directly to the other uniform branch and back. So it's a highly unstable system. Okay, so, and again, that's very useful to analyze all the phenomena we are. And I probably should start with a little bit of an open question or something that's not completely done. So something we're working on actively now is to see how we can apply this picture to the tape spring, which I was speaking of at the beginning. So for the tape spring, the strain, the relevant strain would be the curvature. And you can do all this analysis to build this kind of diagram. The main question is how you get from the shell equations to that 1D diffuse interface or van der Waals type of model. Okay. So I'm done. I hope you enjoyed the lectures as much as I enjoyed preparing them. And I hope it opens up for discussions with you guys. Thank you.
Thank you.
Okay.
Thank you for receiving the relief. And very good.